think we are live. So welcome back, everyone. Thank you for joining us for today's Law Physics webinar. My name is Alejandro, and I'm going to be your host. Today, we're presenting Julia language for high-performance computing by William Godoy. William is a senior computer scientist at Oak Ridge National Lab. William is from Peru, and his background is in mechanical engineering with research interests on high-performance computing, HPC, programming models, workflows, energy and computing, and even a little bit of AI for HPC. He got his PhD in 2009 from the State University of New York. Today, we will have a glance of one of the, in my opinion, the most fascinating programming languages we have in the market today. So remember that you can ask questions over email through our YouTube channel, and then the questions will be read at the end of the talk. So without further ado, we will turn to the time to over William. And thank you for joining. Thank you, William, for being here.
My pleasure, Alejandro. Thank you so much. I just want to mention that, so I'm going to start sharing my screen. I met Alejandro at Los Alamos. I gave a modified version of this talk, of course, right? And he invited me because he saw that, you as a hardcore physics audience can appreciate what, the Julia language is providing and what we're going to be talking about today. So yes, as Alejandro mentioned, my name is William Godoy. I'm a senior computer scientist in the Computer Science and Mathematics Division at Oak Ridge National Lab. Today, we're going to talk about the things that we've been doing, not only on the Julia side, but also what we do here in the high-performance computing side and why we took an interest on the Julia language for science. I'm going to go very fast on some slides. So I'm going to share the PDF after this, with all of you. But I think I'll try to be targeted because, this is more for a general audience. So a little bit about myself, just to give you some background, as Alejandro mentioned. So I studied in Peru back in the day. It's been a while. My background is in mechanical engineering, but I always done things on the computational side. So my interest always been using high performance computing. More recently, we have funding for AI and what it means for all the things we've done in the past decades. So I also, kind of have a road before I got to Oak Ridge. I was a NASA postdoc using their supercomputers back then. Things have changed dramatically. Right now, we see the introduction of GPUs, and we have to constantly adapt to this world. And this is part of the motivation why a language like Julia is going to help, us scientists. Being at Oak Ridge since 2016 is the longest I ever been anywhere in my life, close to a decade. So I'm very proud of that. I'm a IEEE senior member and ACM member, so that's more or less a shift I had in my career, right? Going from mechanical engineering. I still have my ASME membership, but I'm mostly active on the high performance computing side of things. Now, why HPC? Because, and this relates to Julia a lot, because Julia proposes to be high performance from day one, right? Like the Julia code that you write is closer to ideal performance, right, to those in compiled language. And that's part of my interest, right? Because programming these systems is hard, it's not easy. And we're trying to solve really big problems, right? The typical way we do, especially people that do particle things, and is that we start, experimenting our ideas, and then all of a sudden they don't scale on our workstation, and we realize, oh, I need to go HPC. That's the gap we want to close, right, in our efforts. Current projects, if this doesn't mean anything to you, that's expected. But think of it as us in the Department of Energy. We have to navigate, the different requirements from our sponsor, in which our projects are, 2-3 years, short-lived, 4 years. Some projects span longer, like the exascale computing project. But these are the areas I'm involved and try to cover. Best way to get to know any of us, of course, look at our publications. So you're gonna see a correlation between, the work we do and our sponsorship. I'm gonna go quickly because I have to talk about my employer. Oak Ridge, we're at Office of Science Lab. We, well invested in science. And also for you to understand where I'm coming from, we have wonderful user facilities. Many of you probably heard about, from your experimental colleagues on the spallation neutron source, and, CNMS, nanophase material sciences. So we do the things universities and industry don't do. We try to close that gap with big government investments. I work closely with the supercomputer and different architectures. So why supercomputing? And I'll go quickly because it's a league of its own. If you look at the top 10 supercomputers, they essentially, try to solve problems nobody else can ever solve in the past. So we're trying to push the envelope in computing. Of course, AI has changed that a lot, but those are different workloads. In our case, we're still like very much involved into science, solving science for parallel computing. And let's not look at these systems as yet another cluster, right? Because we are going to find a lot of problems, that we never seen before. So here at Oak Ridge, we host, at some point, the fastest supercomputers in the world. Frontier is number 2 today. So we are what is called a leadership class computer. Leadership meaning like people who access the systems don't need 2 or 3 nodes. They actually, in their proposals, they have to justify why they need, the entire system. So to solve different, new problems, different problems. So many people with a physics background actually use, quantum Monte Carlo. I was involved in one project, use this type of systems. We're part of something larger, and that's how I met Alejandro, right? At Los Alamos, we're part of the DOE, the Department of Energy National Lab Network. So I promise this is the last slide, and we're gonna jump into Julia, right? So why Julia, or how is that different? A lot of the questions I get is like, oh, is Julia a replacement for Python? Oh, is Julia a replacement for, Fortran? Or why Julia? Nobody uses it. But we find it very interesting their value proposition, right? And why we took a step, because traditionally DOE have paid for, it's interested in performance portability. Write your code once and deploy on different systems. We'll talk about it later. But in this case, Julia provides those capabilities, but it's paid by industry and academic contributions. So for example, we see now that it's making headlines. It's still a young language compared to other ones because it started in 2012, but you start hearing more about it as you go. So for example, NVIDIA, right? Largest company in the world nowadays. It lists Julia with the big guys, right? With C++, Fortran, Python, the CUDA. We see that people are making investments, right, in industry. They have a commercial side. So that's why we also took a step to see how we can leverage what they already have. Personally, what brought my attention is this, the thing on the left-hand side, that I can write some function, I can actually lower it. I can see what the compiler is trying to do, which is LLVM. And it gives me more certainty or control of how this is going to perform, right? So you cannot do that with other languages easily. You can do that with C++, of course, with compiled languages, with Fortran. It's a little bit hard with Python. So for me, it kind of covers a gap, right? And it's interactive. So I always throw 2 jokes, right? Oh, Julia is what modern Fortran should have become, and not that object-oriented thing they throw that no one uses. And the second one is, oh, this is just MATLAB on top of LLVM, right? So you can do your science in one ecosystem. Anyway, so for those who are familiar writing proposals, and we are actually very much into this mode of following the Hallmeyer Catechism, right? So the Hallmeyer Catechism is a set of questions. I think I put the link here, or no, but just Google it, sorry, in which we try to answer these simple questions before we actually, try to go deep down in details, right? So Hallmeyer Catechism for Julia. What is Julia trying to do? It's not really a replacement. It's more like for people that want to prototype or want to test ideas on a high productive language like Python or R or MATLAB, but they also eventually need performance, right? Then you have to migrate to C++ or Fortran. And also, that kind of adds fragmentation, right? You need a team developing, you need a team prototyping, and then they need to talk, right? And C++ and Fortran, they're not easy languages, right? Maybe Fortran, but Fortran was great for the era of CPUs and Moore's law. Now that you add heterogeneity, now that we code in 2025 for GPUs, for tensor cores, for ARM CPUs, it becomes harder. So how is it done today? That's the other question, right? Python, a lot of complaints, is slow, fragmented. They're making advances, right? They're removing the global interpreter. They're moving in that direction of, okay, we need people need performance, right, in Python. And also combined with C++ or Fortran. The C++ is very complex. It's a systems language, right? Very powerful, but you need to narrow down to what you need, right? C++, a lot of the complaints is how do I debug C++ templates? How do I, do my packaging? So this also comes with the complex in the ecosystem. Traditionally, Python, C++, and Fortran, they never care about these aspects, right? Packaging or it's taken care of by third parties, right? So when you enter the world of C++, you need to learn other things like CMake or Makefiles, the libraries, the packaging. Are you on Red Hat? Are you on Ubuntu or Debian? Those kind of complexities show up, right? In Python, do you pick Conda? Do you pick, I think there's like new packaging system, UV, pip. None of them promise interoperability, right? And also computing is hard outside x86 CPUs and NVIDIA GPUs, right? We have a big machine with AMD GPUs. We're still figuring things out, but they're making a lot of progress. So what is new? Julia is built on top of LLVM, so it's compiled. I really think they made the right decision because it has a LLVM1 essentially. I'm going to explain what it is. And it has a rich open source ecosystem and community. The nice thing about it is that you talk to somebody in the Julia community and they will understand, okay, you're using it for science and performance, right? And as I mentioned, investments in industry. Now, who cares? I think my current audience, right? Scientists or people like me who I just want to prototype my ideas and get my paper out, right? That way, if you don't have to worry about, packaging or debugging things or things like that, you can be more focused on your science, right? You have the things that Fortran provides, but also, the productivity of Python when things go well. What are the risks? I get this question a lot. Like, okay, if I write my Julia code today, is it going to be supported in 10, 20, 30 years? We know Fortran will be supported because we build a critical mass, right? But Fortran is a government investment. I attach here a report from Los Alamos, right? What does it mean to maintain Fortran code and what are the risks? And of course, there's now more popular options, right? People just, when Python might be good enough, right? They use things like Numba or JACC or PyTorch. Nowadays, we look into Mojo. I'm going to mention that as well. But when it comes to sustainability, I think that as they build critical mass, fields rarely go away. We still use COBOL and Fortran. As long as somebody's making good use and somebody's making money out of it, you're gonna see that. And Julia's been growing for the most part. So I would say risk is low in the sense that they also depend on LVM. So let's talk about that. Yet another language, right? I attached the famous cartoon. I promise I'm gonna go low level as from this high level explanation. This is a timeline of my career. All of you will probably have their own. And the thing is that I have to reinvent myself, right? Every single time, all of us, right? There's new technologies that weren't there at different stages of my career. So Julia is essentially why we do this because we are trying to solve modern problems, right? Fortran is not solving a modern problem, so it's solving a very old problem. But now we keep inventing new tools, productivity, and things like that. So a little bit of the landscape of where I come from in high performance computing. So we can divide scientific software, and I would assume most of you are familiar at least with one of them, in two buckets, right? Performance languages, C, C++, Fortran, and then high level, right? And if we want to make things parallel, if we say, okay, this is too slow for serial computing, right? I need to take advantage of GPUs or CPUs and things, or TPUs, who knows, right? AI accelerators. A lot of the choices we make are not because of technical decisions. They're mostly because, oh, I know the right person that knows how to program Numba, right? Or I know the right person who knows C++, and you're able to use those resources. And there's a plethora of those options, right? Do I code for NVIDIA GPUs? Do I use OpenACC? Do I use SQL, or things like Cocos that provide portability? It's okay if you're not familiar with these terms, but the thing is that there's tons of options, right? But in DOE, we don't really want to be vendor locked in, right? We want people to write our code and deploy on different machines, as I mentioned. So 20 years, more than 20 years ago, actually, LLVM, right? Most of you, if you compile code, you're familiar with GNU or Clang or Flang LLVM, right? So LLVM is a secret sauce, right? It's a technology Chris Latner came and that enable all this, proliferation. They essentially redesigned the compiler, and of course he joined Apple around that time, and you have a great idea and you have Apple's cash, and then boom, things will work out. So what happens is that they actually separate the layers of a compiler and they get a nice backend that people can reuse. Backend in the compiler sense. So you can plug in your front end language. And that's basically what Julia is. It's a front end to LLVM. And guess what happens, right? After a few years of developing LLVM, you start seeing that, oh, vendors are adopting it. This is the unifying force, right? So Julia comes, if you look at the plot here, it started around 2011, 2012, I believe. That was the first, alpha version. And when people already saw that, oh, this LLVM is the winner, it's reliable, right? People have been adopting it, start adopting it. So in today's world, you can download compilers, proprietary vendor compilers. Like in the past, I have to pay for Intel compilers, right? Because they're also based on the open source LLVM, and it kind of democratized this world a little bit. So what does it mean? I'm going to skip this a little bit. So one of my favorite statements come from Bacchus, creator of Fortran, right? At some point, all of us have bumped into Fortran. Is that he was not only trying to solve a technical problem, but an economical problem with low cost. So Julia comes from the same, philosophy in which it's about productivity, right? Where they give you the tools that you need in one language and ecosystem, just like Fortran did decades ago, right? To translate science into, translate your ideas into actual science. So I think this is the one of the key slides, right? Going more technical. So Julia, it's the value proposition, right? Ultimately, you give the value for your science. It's designed for my take, scientific computing and data science. So think of it more of a domain-specific language, right? In which, oh, we're narrowing things like MATLAB, right? We're narrowing things down for what they call, they meaning the Julia Hub or MIT technical computing, right? So we separate these two things. That's kind of covers most of the things we do, right? We generate data, we run simulations, we test our ideas, and then we analyze data, and we use Python for that. So Julia combines those two things. But I think the difference is that you can actually write performance kernel codes, right? Because it's based on LLVM. So the message we've been putting in the community is that Julia does not replace Python, right? We're not asking people or throw away your Python code. Now, Python is super important, right? Especially in AI, PyTorch, things like that. The entire world uses Python, right? But it's mostly for people that need this capability, need to be more productive when you prototype something and then you want to get into production. Production meaning like run at scale or at least run it on a GPU, right? And you don't want to rewrite your code every single time. So it kind of replaces that loop. And how? Because as I mentioned, you can write your kernels. LLVM will lower it to CPUs or GPUs or if needed. It has a packaging ecosystem. So one of the questions I get always is there something like Conda in Julia? And my answer is yes, it's called Julia. So you can go inside Julia and track the packages and that you need and things like that. So and it has a rich data science ecosystem. They have, the FluxML framework. I haven't played much with it, to be honest with you, but it has all the things that you expect, like in the Python world, right? The equivalent of pandas or all the graphical interfaces, stuff like that we take for granted in Python. So what Julia prevents you from doing is essentially give you good access to GPUs, CPUs, parallel computing, also the data analysis stacks, and you don't have to deal with all this big X, vector in which, you have to combine third-party technologies to get your science done. So a brief walkthrough. I'm gonna go quickly. Also, as I mentioned, starting in 2010s, it has a commercial side called Julia Hub, and then MIT is also a major contributor. That's where most of Julia Hub people came out from MIT. It has the first stable release was in 2018. I was aware of that in like around 2015, 16, but I wouldn't use it. I would just play around. I wouldn't adopt it, right? I still have to update this. Now they're in 1.12 as of 2025. It was recently released. It's open source, so it has a permissive license. If you find Julia code, you can copy it and reuse it, analyze it. I really like that aspect. And they have the JuliaCon community summer conference if you want to learn more about the general language. Now, one of the nice things about the packaging system, the ecosystem, is that 95% of Julia packages have some sort of CI, right? So there's a difference with the Python world. I'm going to get to that. And it's been growing in terms of developers and community, things like that. Why? Because it actually serves a purpose, right? As you can see. Also, the difference with things like Python, and don't get me wrong, Python have moved towards this direction. It has adopted a lot of these ideas, right, through third party. So one of the favorite things that I have is that reproducibility is at the core of the language. So if you look at any Julia package, you're going to see things like a project Tom, right? In Python, they call it pyproject.tom, right? To be compatible with PyPy and things like that. So essentially, that's your starting point. Oh, what are my dependencies? Oh, this is a unique, what is the current version? What are the things that you need before you even look at the source code, right? So it sets things like, your environment. You can do interactive things, right? So one of the, let me actually pull this out because I always like showing technical things. So you can define a function here, right? And say, let's put it this way, right? And then this is what I was talking about. Like I can do more things with it at the lower level. So I can actually inspect the code. So you can do this interactivity, no matter what you do. In my case, I want to see this. In your case, you might want to see a plot. You might want to, do kind of things. Packaging is here with the closing brackets. You can see the status. What are the current packages in the global system? So you don't need to go with Conda or pip, but it's already there. That's kind of what I'm trying to show. And I'm on my Mac. So going back to killing you with PowerPoint. So Julia is just in time or ahead of time compile, which for the most part is just in time. They're still working on ahead of time compilation. By ahead of time compilation, I mean traditional compilers like the way you would use C++ or Fortran. You compile first, and then you need a runtime to run these things and execute your programs. It has good integration with, things like, I forgot, testing environment. This is, for me, super important because if you look at the bottom right, you can, just like in Python, right? You can like PyTest or unit test. You can do that easily, right? That saves you headaches later. And all this is done through powerful metaprogramming for code instrumentation. So if you're testing your idea, you have your algorithm, right? But then you want to learn more about your code, right? But it doesn't belong to your domain. So for example, oh, I want to profile my code. I want to time my code. Or I want, like I show you, I want to inspect what the compiler is doing. Am I using the right types? It's a type language, by the way. It's dynamic, but it's type, unlike Python, right? Um, those kind of things. You can instrument the code with a rich metaprogramming macro system. And interoperability is super important because writing code is a big investment, right? So if you have a C interface, every language talks to C, right? You can easily interact with C using C call. I actually wrote some Julia wrappers connecting the vendor tool libraries, to get energy measurements, things like that. But as long as I provide a C interface, oh, I can reuse that. I don't have to rewrite it or do those kind of things. So there's already a lot of code in science, so we don't want to rewrite that. We want to solve new problems, right? Bring new ideas. So Julia really doesn't replace Python. What I'm trying to show with this slide is like it replaces things when Python is not enough, right? When you hit that wall, that performance wall. Like Python's great, but this code shouldn't take 1 hour. Those kind of things, right? Uh, that's really the niche world, right? And in which you can wrap things around. How do you make Python faster? Well, pick your option, right? There's so many options here, and none of them, it's a fragmented world, right? None of them promise interoperability. So for example, because you use NumPy, that doesn't mean necessarily it's going to work perfectly with, NumPy or JACC or all the options that you have here, right? Canonical way is just wrap it around C++ or C libraries like, PyTorch, things like that. But then you have to jump into that ecosystem. What I'm trying to showcase here also the difference is there's a website tracking like PyReadiness, which means Python comes, it's more reactive in the sense that Python releases a new version, right? Like 3.14, for example, right? They remove the global interpreter log. That doesn't mean the whole ecosystem is ready, right? That means that, oh, the language comes first, now the packages will follow. So it's up to each package developer. Julia is a little bit more on the preventive side, in which, oh, we're gonna do a new release, then packages can start trying it, can start using, can do CI. So it depends also on the package maintainer, right? So you have to establish that connection regardless with your package dependencies, right? But it's a closer dependencies because you won't see this fragmentation in Julia. There's only one package that does CUDA programming, one MPI, one, especially in niche things, right? Like you will see one data frames, those kind of things. So we also look in our research on the module language and try to understand this. We are part of a bigger project, of course. We don't do just Julia, one language. We do things for the Department of Energy, and we're lucky that our intern is going to be presenting that in one of our top conferences, the supercomputing conference, which is equivalent for you to APS, kind of thing, one of the workshops. So all of you are welcome to look at that. So in a nutshell, why Julia? Think Python, Fortran, but now imagine that for our case, it worked well on HPC. So you can access parallel computing, if you need it. You won't have to wait too long because your code is actually compiled. Just-in-time compiled technical language, so the syntax is very aligned with your science and math. Interoperability, as I mentioned, don't rewrite, just leverage. And it has good support for ecosystem stuff. So all the makes Julia a good ecosystem. Again, think of MATLAB, but open source, and you don't have to pay the license, right? So now I also have to show the other side, right? Why not Julia? Because you already have your investment done in another language. If you have your Fortran code, that it's stable, it's been running for decades, why ain't broken, ain't fixed? It's because you don't see the long-term return on investment, right? You see that there's a package that you need, but there's no support. It's stable, but also Julia is stable, but it's also not a standard. Some people have asked that, is Julia standard? I would say for practical purposes, it is, but technically it's not. You don't have a standard committee, right? You only have one implementation of Julia. And also because the ecosystem might not be mature, at least in HPC, because in HPC we're a government investment, we kind of like have to wait for, you know, our grants to work and see if that's supported, right? If it's not on the commercial side, we have that disadvantage. So maybe it's out of scope for what you need, right? Maybe you need, but you're happy with Python, and or maybe you're just comfortable in another language. So these are some of the reasons that we collected in our work on exploration. Let me see the time. Okay, so what do we do actually? So I talk about Julia general, but here in our lab, we're trying to close that gap again between the language, the general language, and trying to run it on high performance computing. So this was a work that we did 2 years ago. Our initial exploration is, okay, Julia have all this, but does it run on Frontier, on our, at that time, fastest supercomputer? And that was a research question we tried to answer. HPC is a science on its own. So, you know, we don't take this for granted, right? That's something I learned transitioning from, you know, more of my mechanical engineering background into HPC. The question was yes, you can run it on Frontier, but it's not there yet, right? There were a lot of gotchas, but it was actually a pretty good experience overall. We wrote a 7-point stencil kernel. Sorry, I haven't talked about the application. We run a grayscale diffusion operator, so you can see here it's a PDE solver, the classical like, you know, Poisson operator. You know, you end up with a Laplacian, so nothing complicated. And this is a classical 7-point stencil. When you outline this 3D array in memory, then you get this, you know, access memory pattern. So it's a memory bound algorithm, which means your performance is limited by how you access memory, how often you access memory. What we found here in this slide is a little bit convoluted. The important part here, you have the Julia code. It looks very much like a hybrid between Fortran and, you know, CUDA, but, you know, HIP. But we are using vendor-specific implementations. What's important about here is that it worked with some of the profiling tools that the vendor provides, but we found a gotcha, right? Like, oh, performance wasn't there, right? Now it was half of what the vendor will provide. Now you don't want to try to be, you know, close to the vendor because the vendor knows things we don't know. This is all open source, remember. But you know, we did all the analysis that you can do with, you know, the lower level, the compiler, things like that, the profiler. But we still have to close that performance gap, if possible, of course, right? So this was a good paper. We also measure things like overhead on just-in-time compilation, things like that. So we're going after, you know, maximum performance, right? Some people are happy with just having half of the performance. Now, I always joke that think of it as if it was Python, right? This will be huge. If you write Python code and it's already half of the, without further optimization, half of the performance of the vendor, that will trigger huge highlight, you know, huge headlines in the Python world, right? But you know, Julia is still compiled, so there's room for improvement here. And we tested on AMD GPUs here, and we did all the analysis. We also tested on that paper for weak scaling. Weak scaling means like, okay, you have the message passing interface, which is what we use MPI in our supercomputers so the nodes can communicate. And it, you know, essentially it just wraps around MPI. It's like MPI for pi at that point, right? But we demonstrate that at this scale, it's not adding more overhead than what the system overhead, typical system overhead will give you. So this helped us answer one of the common questions, like what is the biggest run that you've done or people have done in Julia? I honestly don't know, but so far what I see from papers is that we run up to 4,000 nodes of Frontier. Sorry, we run up to 512 nodes of Frontier, which is 5% of Frontier. But Frontier is huge. We're talking about 4,000 GPUs, right? I try half of Frontier, which again, I have to block most of the users, right? And it resulted in a underlying lead fabric error, one of the capabilities underneath MPI. So this is way beyond the scope of Julia. The GPUs run and things like that, but I don't want to be yelled at, right? If I'm trying to use half a frontier, and this was good enough for a paper. So on the next, we also tested for parallel I/O. I was fortunate enough to work on this project, the Adios 2 project. So parallel I/O library is triggered by the needs of people in Fusion, for example, people in using climate codes that are big data producers, earthquakes, things like that. So you don't want to waste your node hours or core hours into doing I/O, right? So Adios tries to solve these problems, scaling parallel I/O. So again, similar to MPI, when it comes to moving memory, you're way outside the domain of what language you use, right? So we have good scalability. And something probably more important to you guys is that we were able to do data analysis on Jupyter Hub here at OLCF. So we just run a kernel and do all the Julia things that we needed to do our data analysis, things like that. So all in one language, right? What's not to like, right? I'm going to skip this quickly. If you're interested in our papers, we have preliminary efforts on evaluating Julia against Python, Numba, and understand the difference. Our work is more on the heterogeneity side. So we care about like different vendors, GPUs, ARM CPUs, things like that. So, and part of also the work we do with our fundings on the community side, organize workshops, have interns, things like that, in our conference. So I'm going to skip this. This is just to showcase this. Julia is growing and actually domains, right? Like we have people actually writing community codes in Julia. You can explore the links and see which one relates more to your application. And there is an HPC stack, and we're doing all the things that we do. Also, I ran a workshop at Oak Ridge in 2022. The world was very different. There was not ChatGPT or anything. No one was using Julia, but we had 100 registration. People were like hearing about it, but they want to learn what is it about. Fast forward 2 years, and we start seeing people actually using it, right? Like we have the same version of the workshop, but now we have, I believe, from the data, like close to, I don't have it here, but close to 16 presentations of people actually using it for the science. So that's big growth in 2 years, and that's kind of why we are invested. Now, let's talk about parallel computing a little bit, because that's also part of our investment, JACC, right? What is JACC? It's essentially a way for you to, if you're not familiar with these concepts, we're going to explain that a little bit. Julia has put a lot of backends capabilities. So you can run parallel code, mostly parallel for loops. I'm going to explain that on CPUs and different vendor GPUs, right? And as you can see here on the right-hand side, JACC builds on top of those. We try to leverage what their industry investments. So my employer or my sponsor, the Department of Energy, didn't pay for anything below JACC. And that's important. JACC tries to leverage those. So we provide a parallel for and a parallel reduce construct so people can actually parallelize their codes without having to learn how to program GPUs, without having to fine-tune necessarily. We take guesses, of course, but it puts you there. It puts your code in there. So we hide all this low level, on this device-specific things like memory, granularity, blocks, and thread. So you can actually just execute your parallel for. And we're trying to build a community. We have a paper out there, and we organize meetings or just reach out to this. What I mean by this, one of the basic fundamental blocks in our codes and science is a for loop, right? So a for loop, that's why we move from CPUs to GPUs, because it's a very common use case in which I have a loop or multidimensional loop, right? And each component, each workload here inside that loop is independent. So my ij doesn't necessarily depend on the previous I or the previous j. So that allows you to move to parallelize on CPU and GPUs, as you can see here. So this is what we call coarse granularity, and this is what we call fine granularity. A GPU just have more cores to parallelize, right? So you can focus on this ij specific. So imagine that each square here is focusing on just one ij, but you have thousands of those. So it scales when your domain is big. Whereas when you're using coarse granularity, you only have a handful of powerful cores. And that nowadays are limited by Moore's law, and they cannot get any faster, as we used to. So what we do here is we turn this parallel 4 to use JACC into a parallel 4 construct in which you are passing first the domain and then your workload. In this case, for example, I encapsulate and call it into a function, add to the, or we call it the kernel, right? So this in a rectangle, this expression, that's a kernel, that's a workload, right? Like the 7-point stencil we show. Ideally, you write this code once. Let me see you to the next slide. And that will run on CPU and GPU in parallel. You just select the backend. You select, oh, I have like in my computer, I have a CPU, an Intel CPU, and I have an NVIDIA GPU. Oh, I can run the same code. I can only write once. And we also have high-level constructs like that you will have like in, for example, NumPy, right? Oh, give me an array, a multi-dimensional array of ones or zeros. We have tons of examples and training. You can construct an array, of a certain size. Now, how is this possible? It's because JACC is metaprogramming. So at this point, we haven't concretized. It's the first time we compile the just-in-time compilation that a JACC array or a parallel 4 is going to morph into the backend, right? So JACC is going to go into CUDA, or JACC is going to go into the AMD GPU package if you have, if you selected that backend. So two main components, you allocate your arrays like you will do if you're coming from Fortran, you're familiar with this concept, or you use NumPy. You don't have to worry about, oh, is this a CPU array or a GPU array? No, just write your science, right? And then kernel launching. We have parallel reduce and parallel 4, which is what I explained in the previous slide. So the backend selection is done outside the code. You just call, this function and say, oh, I have an AMD GPU. I want to test that, right? And we have a full example on the Grayscale, the code I show that's the basis on the paper. Maybe you don't care too much about this, but this is kind of like what we do under the hood. This is not exposed to end users, but then JACC is open source. You can look at that. How does it work? Some developers are interested, right? What we do is simple. We just redirect your code to whatever backend is needed. As you can see here, for example, we build on top of CUDA, so it's going to branch into those things. It's equivalent, so you don't have to do if-def like you will do in C++ and things like that. So Cocos does the same thing for C++, but we leverage what Julia provides in the sense that, you can write multi-dimensional arrays. You can, reuse like the standard library, which is very rich in the mathematical sense, Now, but this is HPC, right? Our sponsor comes and like, yeah, but what is the performance? So we try to answer those things. I put this on the papers that we published in the last few years. So our goal is to verify that we are not really adding any overhead, compared to our backends, or the overhead is something that people can live with. I'm gonna go quickly. Put something on the. I have a few minutes if I can, Alejandro. I know that our time is up, but now what do we care about this? We don't really care so much about the software implement. Oops, sorry. I polluted my. Sorry, I have to. So what I'm trying to say with this slide is, okay, then you put something out there in the wild on GitHub. Guess what happens? People come, they see, oh, I can use it for my problem, right? We seem interest on places, like I showed in previous community codes written in Julia, right? Like Surface comes and we had a great conversation. Say, oh, we saw you guys have this JACC implementation. Maybe that's something we need. And we are trying to modernize our Fortran code so it can run on different vendor GPUs. And I see you guys have the basis. So they were kind enough to share with us. We didn't even talk to them until they show us this plot and say, oh, we use JACC and we're able to run our lattice Boltzmann codes. And these are the results, right? You can see their code blast JACC using JACC on the green. So they were able to get that portability and the performance, right? And they didn't have to be locked into one vendor. They didn't have to, write two separate codes for 2 or 3 different vendors, and so on. So they found that very helpful. That's what we're after here, the impact. So if you guys decide, oh, we're going to use JACC, and that help us. My colleague Pedro here, he's part of the team, of course. He has put all their exploratory things. He saw that, oh, with Julia, we can leverage shared memory, caching your data so it's faster. A typical example is a convolution operation, very common in AI operations. So, we try to leverage those kind of things that Julia provides that we can incorporate in our HPC world. The paper is there, was accepted last year. We have some ongoing efforts, but we're a small team, right? We are trying to be targeted and who is using JACC and what is it that they need. We, of course, cover the scientific aspect. We're happy to work with interns. We have the best poster, supercomputing. Pedro presented his paper last year, at one of the workshops. So we move in our own HPC niche. Work done by our colleagues, they grab JACC, and as you can see, what the appeal here is that you write your kernels and they look very scientific, right? Unlike in C++, in which you have to adapt to the system language or you use a library. But in this case, because Julia is already scientific, my colleagues Philip and Steve, they developed this proxy app to simulate some of the workloads that one of our facilities, experimental facilities, SNS, the spallation neutron source, needs and can leverage the other facility, the high performance computing facility we have here. And we had a paper that essentially demonstrated that scientists can write code once and take advantage of HPC, because most of the codes we have on the experimental side are for CPU only, applications. But, at some point we're going to hit that wall with the end of Moore's law. I'm very close to the end, where to get started. Be patient. I just collected some resources. We give training, of course, at least to get you started. So pick a gentle tutorial. I found this one from Zero to Julia very, very gentle, very, very a good introduction. I use Visual Studio Code. That's the officially supported IDE. I play with also Copilot, because Julia is a simpler language. Copilot is able to pick a lot of the patterns. So it's really helpful to code in 2025 using all these tools. Patience, community reliance, I think that's also one of the difference. Julia, as much as Python is general purpose, you have to find your own little community inside Python. In Julia, you're able to connect faster because, okay, these are mostly scientists, mathematicians, or people that need performance, right? Or people doing AI and data analysis. Again, as I mentioned this, I use Copilot. That's another part of our research, right? I myself, I pay for the license, and it actually auto completes a lot of the cool things. This might not be perfect, but it puts you there, right? I'm gonna wrap up now. So as for PST, this is one of the projects that funds these efforts. Of course, it's not just Julia. The Department of Energy needs everybody, right? And I'm glad to be working with a larger community. I'm co-PI right now of this project. My colleagues Keita Karanishi and Pedro Valero are also leading this effort. And we support things like COCOS, OpenMP, OpenACC, other programming models that scientists use, that scientists need, LLVM efforts, things like that. MIT is part of also this project. And we're also part of something bigger, the Consortium Advance of Scientific Software. So we try to steward the software that DOE puts out, all these underlying libraries for high performance computing. But Julia is part of our incubation in this ecosystem. See where this goes. Last but not least, we work a lot with interns because they are the important people that can do all this technical work. They have the continuity. So we're happy to talk if people are interested, or just reach out and if you have any questions. So in summary, we've been showing the exploration we've done on Julia for our needs, at least in the Department of Energy. We put the JACC framework so it can help our scientists interested in using Julia. And then we're trying to figure out what's Julia place in DOE, right? We have new applications, new directions, right? Like quantum computing, energy efficient computing, AI, of course, right? What does it mean, Julia, with LLM? So all this new world and new directions kind of like, help us get situated. I just want to thank a lot of people, but in particular, Alejandro, for this invitation. I hope this was helpful and happy to, I, of course, want to thank my sponsors and happy to answer any questions from the audience. Thank you very much all for attending. So.
Thank you, William. This was great, and exactly I think for law physics is a great addition. Before I see if there are questions on the YouTube or people here in the call, I would like to ask you two questions that might be a little bit general. So when is the next workshop to advertise it, or do you guys have it planned or not planned yet?
So you mean workshop here at Oak Ridge?
Yeah.
So we haven't made plans because we're very reactive in terms of funding. Right now we're focused on AI, things like that. So we're gonna wait until the dust settles. And yeah, no, I'll keep people in the loop. As you saw, our cadence was every 2 years because every year might be too much,
Yeah.
But maybe next year will be. I'll keep you in the loop. But if
Sounds
it's
good.
next year, maybe the year after, and we might try to also put it together with other efforts. Like as I mentioned, we look into Mojo.
Yes.
There's nowadays Triton, things like that, right? So Python is important. So we also try to put it together.
Wonderful. Okay. Anyone in the call with a question? Well, I don't see any hands here. So I have another question. So I have used Julia in the past, but mostly threads within a node, and it is working as expected. But then I have always been a little bit reluctant how to go from the MPI type of thing. Like now I want to work on different nodes. So the thread, when they share memory, is working like a charm, and many of my students are using that. So you think, if I understood this correctly, what we should be doing is JACC then to
So
start rewrite the code in a JACC cocos-like way, and then that will allow us to go like to different nodes and connect several of the nodes. Is that
yes. So to answer usually the way we actually interact with people, we show them like the portfolio, right?
right?
So Julia, in the sense that Julia has two what we call performance portable layers or libraries, right? One of them is kernel abstractions, which is kind of part of their Julia GPU organization. But we look at kernel abstractions, and we all know each other, right? And the value proposition is that they use a CUDA model. Essentially, you have to learn how to program in CUDA to use kernel abstractions, right? So imagine if you have portable CUDA, right? For GPUs, it's fine granularity, right? And JACC comes more from the side of Cocos, right? Like, scientists shouldn't shouldn't read the CUDA programming guide, when they have a parallel for loop, right? So you choose depending on who you are and things like that. And also, JACC, we're trying to provide the support here from the DOE side, right? Eventually, we're close to making a 1.0 release.
Okay.
We haven't changed the API for a while, so I want to say the best way to find out, we don't want to push people, right? Like, just go play with it and see what.
Okay, sounds good. Thank you. Let me see while I check the YouTube. Anyone? Oh, I see a question in the chat here. How do you see Julia evolving over the next several years, especially in the areas of AI or data science? Will it be distant from how Python and R are evolving?
So I actually gonna, as a good scientist, I'm gonna answer that question with another question. How are Python and R evolving? Right? I want to be sure I'm giving the right answer. So, what we saw on Python, right? It's a general language moving more towards like, okay, we're now in the AI world. People need performance. So they've been actually having this diversity of languages help because they've been reusing some of the ideas, right? Like the Julia community put. R, for example, has a good packaging system. That's something Julia also, adopted. Now Python or Conda or pip, So Python itself hasn't evolved much in that regard, right? It's a high productivity language because a lot of these things don't belong to Python. They belong to the ecosystem, right? The packaging and all these things, right? Like, or PyTorch, Python. One of the things about Python is that most of the Python packages are not written in Python. They're written in another language. So, in Julia is the other way, right? Like, oh, they have if you look at the Julia implementation, it's mostly written in C and Julia itself. So it's all hosted on GitHub. I'm gonna put the link. So and the evolution of Julia or the language, as I see, is because of for natural reasons, right? It accommodates to the needs of Julia Hub. So I cannot speak at that level of detail, but Julia Hub is the commercial side, the company that is essentially deciding on this evolution. The community, of course, is part of that, but they have a business at the end of the day, right? But their business aligns very much with what we need in science. So performance is going to be number one, heterogeneity, GPUs, things like that. It's already there. So I hope that answers the question.
Yeah, we see there is always a typical feed delay. There is another question on the YouTube channel saying, do you have something similar to pandas to analyze data? Or are you aware of something like that?
Yes, yeah, it's called data frames.
Okay.
So when you go to the more commodity kind of general use of Julia, as you can see, we're more on the niche HPC side.
Yeah.
But if you look at the general language, it gives you all the components, right? That like you can do plots, CSV files, JSON files, YAML. So a lot of these higher level software engineering aspects are there. One of the things, let me show you really quick my screen because I think that will illustrate kind of like the power of Julia, right? A little bit. I always use this Gray Scott as tutorial material. You're welcome to look at it. So you can use MPI to go to low level HPC and parallelization and all the things that people from HPC know and are used to that. But you can also do things like read a JSON file kind of thing. Let me actually, I have it here. So for example, right here you can do like a parse arguments, things like that, things that you have in Python. And then you can just parse a JSON file and get the high level constructs like a key value and things like that. So, like I said, that is, I think, the great value of something like Julia, that you can go as low level as you need, or if you're more on the Fortran side, like your functions will look very much like Fortran. You can slice arrays, multi-dimensional arrays, things like that. Think of MATLAB, right? But you also can do things like, analyze this data and things like that. We have tons of tutorials, on covering those fronts, if that makes sense.
Thank you, William. I think we are about to reach the hour, but then I see one hand up. Paulo, you can go ahead, unmute yourself, please. A quick question.
Thank you for the seminar. My question is more on probably how JACC works. At the beginning, you showed a command that lets you see like the intrinsic low-level proceedings of a function that you wrote, right? I don't remember the name exactly. But if you wrote a function with JACC and then use that command, would you see like something, for example, if you were using a CUDA background, would you see the CUDA code or something like it?
No, that's a great question. And the simple answer is you don't. And let me share with examples that some of you might be familiar with. So for example, we have this, we work with interns supporting this Hartree-Fogg benchmark, right? So the way JACC operates, this is a typical user interface, like what you would do if you are solving a physical problem, right? We import JACC with import or using. This is similar to Python. And then we have this macro that will auto-detect the backend that you pre-select, right? So you have this code. If you look at this code, it's your typical Hartree-Fock, kernel, right? For those who are familiar with it. I will say you are more familiar than me. And then, we actually have this kernel. That's what we call it. It's a whole function that is independent. And then we also support atomic operations. So one at a time, just modify one at a time. And then we launch these kernels, right? Using the parallel for construct. You just pass that function and then your arguments. So the magic here is that this code should run on AMD GPUs, NVIDIA GPUs, and CPUs. So I hope this kind of answer your question, illustrate. And where does the detection happen? It happens here. It just after we import. Ideally, we just want to use this, but then we have to work around Julia itself, right? And this init backend allows you to be portable, right? Not worry about CUDA or AMD or be vendor specific, right? So I think if you look at this macro, it's essentially that if else if typical, branching that you have. If CUDA is F also is that kind of thing. So I hope that answers.
Yeah.
Yes, thank you.
Thank you, William. Thank you, everyone, for attending. Stay tuned for the next Law Physics webinars. And again, you know how to reach William if you have more questions, or if you're a student and you want to be an intern and find these opportunities at Oak Ridge Lab. So thank you, everyone, for attending today. And we look forward to seeing you in the next one.
Thank you, guys.
Bye.
I appreciate it.
Okay, we are not live. Thank you, William. This was lovely. Exactly what we need.